Okay, now for the next problem, we've got that BC is 1 more than AB, and AC is 1 more than BD. And this immediately makes me think of this triangle here, which is 3, 4, 5. Now, there's a problem. The question says that this is an acute angle triangle, but let's just work with this triangle anyway and ignore the acute angle thing and then later reason whether it's important. So the smallest side, which is AB, is this one. This next BC is the next smallest, and this AC over here is the next smallest. If it's this triangle, then this will be 90 degrees, and basically B must be equal to D. And then we can calculate what is CD. Well, if B is equal to D, then CD is equal to CB, which is equal to 4. And we can calculate what's BD. Basically, BD will be equal to 0. And then we can find the difference between these two, and we get the answer of 4. Now, we're going to have to find out, does it cause a problem that I used a right angle triangle when this is supposed to be an acute angle thing? What I could reason is I could change this length to something ever so slightly greater than 3. And this length will change to something ever so slightly greater than 4. And this length will be something ever so slightly greater than 5. Then this thing will be still pretty close to 90 degrees. And this value of D will still be pretty close to this value of B. And in other words, all of the lengths will not change very much, and the length of CD minus BD will still be approximately equal to this other value that we found over here, which is 4. So that's one way to look at it. Another thing that we can note is that this is supposed to work for any acute angle triangle. So it's supposed to, this difference is supposed to remain a constant regardless of what the actual lengths are. Okay, now we have to figure out, is it a problem that I chose a right angled triangle? Now let's note that implicitly the question implies that this is supposed to give the same answer for any possible acute angled triangle that satisfies this condition over here. Now what we could ask is, suppose we were to take some acute angle triangles that satisfy this condition, and we were to go closer and closer to this case where B is 90. So we might have one where B is, okay, it must be smaller than 90, 80 degrees. Then we might have one where B is 85 degrees, one where B is 89 degrees. And we need to answer the question, is this length suddenly going to change values when we get to 90 degrees? Now, what I could do is I could construct the triangle that has a side length of 3.01, or I could put 3.0001, and this is a side length of 4.1, and this is a side length of 5.01. This satisfies this condition, and it is indeed acute, because relative to each other the sides got closer to being equal, and we know that an equilateral triangle is acute. And this is so close to that if I were to draw this perpendicular D over here, this D will still be approximately equal to B. So we would have that BD would be approximately equal to 0. CD will still be approximately equal to 4. And CD minus BD will still be approximately equal to 4. And so the answer for this triangle must be something close to 4. So the answer must be 4 because there's no other possibility. Okay, I went on about a 7-minute tangent to prove that, well, the difference is indeed 4 for every single case. Would we formally prove this? What we could do is we could make this side length x, we could make this side length x plus 1, and we could make this side length x plus 2. Then we would need to calculate these two lengths over here. Let's call this u and v. But to calculate those two lengths can be a bit tricky, so it might be easier to first calculate this length h and then use Pythagoras to calculate these two lengths from these two right angle triangles. Now to calculate h, what I need to do is I need to say the area of this triangle, let's call it capital letter K, is a half of the height times by the base. But the area of this triangle can also be found by Heron's formula, which for those of you who don't know, Heron's formula is just S, I'll say what S is now, times by S minus this side length, times by S minus this side length, times by S minus that side length, everything over the square root, so that is just on that side, and S is just the sum of these three sides divided by 2. And here we've got two formulas for the same thing, so we could solve for h. Once solving for h, we could solve for u and v, and once we have u and v, we can just subtract the 2. Okay. Someone once told me that once you know the solution to a problem, you can use it to find a shorter proof. Now, technically, we don't actually know what the solution. Don't know with certainty the solution to this problem, but we are almost certain that the difference between these two is gonna be equal to 4. Now, there are two things that we also know. We also know that this 3, 4, 5 is a special case. And so what I can do is I can say, okay, instead of working with side lengths x, x plus 1, and x plus 2, I can arbitrarily make the smallest length 3 plus x, then this next smallest length will be 4 plus x, and this next smallest length will be 5 plus x. Then I still have to work out the difference between these two lengths over here, but instead of working out the difference between those two lengths, I could draw a point on this line over here such that the difference between these two lengths is equal to 4, and then I could do the easier thing of then proving that this point must be that point over there. In other words, I could then prove that this is 90 degrees. Alice also told me it's better to work with multiples of 2 when dealing with these type of problems, because usually that it avoids ugly fractions. So I'm going to just say this is 3 plus 2x, 4 plus 2x, and 5 plus 2x. So what we've got here is, I've chosen this point so that v minus u is equal to 4, and also because this whole line's length is 4 plus 2x, we've got u plus v must be equal to 4 plus 2x. This makes it easy to solve for v. V must be equal to 4 plus x, and also easy to solve for u. U must be equal to x. Redraw all the information. X, 4 plus x, 5 plus 2x. Now, before I go further, what I can first do is just see if this makes sense. Would it make sense if this was 90 degrees? Well, I could calculate this length using 2 different versions, right angle triangles and the theorem of Pythagoras. So I could say this length is 3 plus 2x squared minus x squared, and it's also 5 plus 2x squared minus 4 plus x squared. And surprisingly, both of these simplify down to 3x squared plus 6x plus 9. So this shows that we're on the right track. Now, how could I actually prove it's 90 degrees? Let's just call this length W, and let's call this D1 and D2. Now, what I could do is I could use some inequalities. I could say, okay, let's consider the case when angle D1 is smaller than 90 degrees. Then this over here would imply that W squared plus 4 plus x squared will be, will be larger than 5 plus 2x squared. Okay, making this an acute angle makes this sum of these squares become larger than that length. Also, if this is an acute angle, if D1 is an acute angle, then this implies that D2 would be an obtuse angle, which would imply the opposite, that W squared plus x squared would be smaller than this side length squared, which is 3 plus 2x squared. And if you simplify both of these down, the first one just becomes W squared is greater than 3x squared plus 6x plus 9. And if you simplify down this one, this just becomes W squared is smaller than 3x squared plus 6x plus 9. And that's impossible. It's impossible that W squared is both smaller than a number and greater than that number. So that eliminates this case. And the other case, when D1 is greater than 90 degrees, will be similar. So that only leaves that D1 is 90 degrees.